Hi guys, my name is Armin, and in this presentation I'm going to talk about Penta-Graphene, a new carbon allotrope. First, I will talk about the importance of carbon allotropes and give you a short list of recently discovered carbon forms. Then I'll move on to what Penta-Graphene is, who came up with it, and why it is unique. Since it's a newly discovered material, all of its physical properties must be taken under consideration. So I'll talk a bit about its stability and its mechanical and electrical properties, and I'll finish off with possible future applications. Allotropes are forms of the same element with different chemical and physical properties that result from different bonding arrangements between atoms. The successful synthesis of graphene has inspired considerable interest in exploring new carbon-based nanomaterials. Carbon is probably the most versatile element in the periodic table. It forms a large number of allotropes, such as well-known graphite and diamond. Physically, these two are polar opposites, diamond being the hardest material known, and graphite being used as a lubricant because it's so soft. Chemically, they are the same, both made of carbon. The most recently discovered forms of carbon are the nanocone, nanochain, as well as 3D metallic structures, but the most revolutionary allotropes are fullerene, nanotube, and graphene. The new properties of carbon allotropes are related to the structure of carbon atoms and highlight the importance of structure to property relationships. And for the most part, hexagons are the basic building blocks of carbon nanostructures with some pentagons. The image on the left is an example of a hexagon carbon structure. Structures made exclusively with carbon pentagons are extremely rare. Penta-Graphene, as the name suggests, is composed entirely of carbon pentagons. The unit cell of a pentagraphene contains 6 atoms. It's a 2D structure. The idea behind pentagraphene came from Dr. Qian Wang, a professor at Peking University. She was dining at a restaurant in Beijing and noticed the artwork on the wall showing pentagon tiles from the streets of Cairo. So she had an idea, and she had her students check the stability of a carbon structure made in this pattern. The search for an old pentagon-based 2D carbon sheet began by examining the recently proposed T12 carbon phase that can be acquired by heating the hexagon-based metastable carbon phase at high temperatures. The T12 carbon is the figure on the left. The optimized crystal structure of the 2D pentagon-based phase is generated by chemically exfoliating a single layer from the T12 carbon. The result is the figure on the right, which is a new phase composed entirely of carbon pentagons, forming a pattern known as the chiropentagonal tiling. In the next slides, I'll describe the research done by the team of physicists led by Puru Jaina, and the results were published in the Proceedings of National Academy of Sciences. Pentagraphene has not been actually synthesized, but the published data is the result of the state-of-the-art simulations. Penta-graphene phase is metastable compared with graphene and previously reported 2D allotropes, but it is more stable than some nanoporous carbon phases such as 3DT carbon and 2D alpha graphene. Also, pentagraphene is energetically preferable over some experimentally fabricated carbon nanostructures such as the smallest fullerene, the C20, and the smallest carbon nanotube, implying that the 2D pentagraphene sheet could actually be fabricated. In the published paper, the authors assessed the effect of lattice distortion on structural stability and showed that the linear elastic constants of the stable crystal obey the Born stability criteria. Max Born published a book with co-authors that stated the generic requirements for elastic stability of crystal lattices. The physics behind this is far too complicated to get into here, but the study does suggest that pentagraphene is mechanically stable. The thermal stability of pentagraphene is examined by performing ab initio molecular dynamics (AIMD) simulations. The goal of this simulation is to derive classical molecular dynamics of this pentagonal structure. The results show that pentagraphene sheet can withstand temperatures as high as 1000 Kelvin. The lattice dynamics of pentagraphene are studied by calculating its phonon dispersion. A phonon is a quantum mechanical description of an elementary vibrational motion in which the lattice of atoms or molecules uniformly oscillate at a single resonant frequency. In classical mechanics, this is called a normal mode or a positive frequency for the oscillation. Negative phonon oscillation frequencies are called imaginary modes. The absence of imaginary modes in pentagraphene confirms that it is dynamically stable and very similar to graphene. The most interesting fact about pentagraphene is that it has a negative Poisson's ratio. When a material is uniaxially loaded in tension, it extends in the direction of the applied load. So if you pull on the end of a rubber band, it stretches out horizontally, but it gets thinner. A rubber band has a positive Poisson's ratio, which you can see in figure A. Pentagraphene has an anti-rubber-like quality. When the force is applied on the end of pentagraphene in the x direction, in the nanoscale of course, it expands in both x and y directions. This is the negative Poisson's ratio, which is shown in figure B. The ideal strength of a material is the maximum stress that it can sustain and critical stress for crack and dislocation in the material. When the applied stress exceeds the ideal strength, the crystal structure will collapse even at zero temperature. The ideal strength of a pentagraphene is calculated with the variation of stress with tensile strain using the different cells of the crystal. The maximum ideal strength calculations show that the strain at the maximum stress is 21%. However, this doesn't account for the phonon instability, which brings the maximum ideal strength to 17.2% compared to 14.8% for graphene. The authors called this ultra-high ideal strength. To study the electronic properties of pentagraphene, researchers calculated its band structure and the corresponding total and partial density of states. The presence of the sp3 hybridized carbon atoms spatially separate the orbitals of sp3 hybridized atoms. This stops the full electron delocalization and creates a finite band gap. So pentagraphene is intrinsically an indirect band gap semiconductor with a band gap of 3.25 eV. That's almost 3 times the band gap of silicon. Pentagraphene can also be considered a quasi-direct band gap semiconductor, but it's difficult to determine this conclusively without actual experiments. Now, partially degenerated valence bands lead to a high total density of states near the Fermi level, which according to researchers means that in theory, superconductivity can be achieved in this nanosheet full fold opening. The electronic properties of carbon nanotubes are closely related to those of graphene. Due to the gapless semi-metallic feature of graphene, the electronic properties of carbon nanotubes are highly structure dependent. It is difficult to fabricate individual carbon nanotubes with different conductance, as in metallic or semiconducting, to using nanoelectronics. But pentagon-based carbon nanotubes, pentatubes, are formed by rolling up pentagraphene sheet or the 3D structures of T12 carbon that I talked about previously. Both of these are calculated to be dynamically and thermally stable. It's highly probable that the pentagraphene-based nanotubes could be semiconducting regardless of the structural form of its individual molecules, so it would just be much easier to fabricate them. The results of the discussion of this new carbon allotrope is based only on theory and computer simulations. Pentagraphene has not actually been synthesized yet. But given what we know about carbon forms, it seems very likely that it will be fabricated, and if so, it will outperform graphene in many important ways. To summarize, pentagraphene is thermally, dynamically, mechanically stable. However, it is thermodynamically metastable, meaning it doesn't have the stable total energy of, say, diamond or graphite or even graphene. It has a negative Poisson's ratio, which is a very unusual but exciting property. It is intrinsically semiconducting, so it would be much easier to fabricate for nanoelectronic applications. The applications of pentagraphene would be numerous. It can obviously be used in electronics. It can be used in nanomechanical applications such as deformable variable stiffness material or in biomedical devices formed of ultra high strength and flexibility. Thank you for watching.